Hello friends, welcome to our channel. Let's have a look at today's daily challenge problem. Find elements in a contaminated binary tree. Actually, this problem is rather easy, I would say. So if you realize what things matters, so here actually, so only the structure of the given tree, that is root, matters. So it does not matter, no matter it's contaminated or not, right? So we'll see this point, and this observation also determines or hints how to do the coding. So our plan in this video will be the following. First, I'm going to write a solution that will be timeout. And then I'm going to go to the solution we want to present. So here we are given a binary tree, and the root value is 0. And then for the left node, its value is going to be 2x plus 1 if it exists. For the right node value, it will be 2x plus 2 if it exists. So the binary tree is contaminated, which means all the values have been changed to be -1, right? So we want to implement the findElements class, which contains an initializer and also a find method. The find method check if target is in the binary tree or not. So if you look at the examples, so actually it's rather easy to interpret. I'm not going to go to details. So here, the height of the binary tree is less than or equal to 20, right? This basically tells us the size. So you can think of 2 to the power 20, roughly the number of nodes. So this one further restricts the number of nodes. It's bounded above by 10 to the power 4. So this actually constrains the problem size. So this is the number of calls made for the find method. The target is in between 0 and 10 to the power 6. So with that said, I guess we are ready to do the coding. So as I mentioned, I'm going to do two codings. Let me copy one and put it here. So I'm going to call it V1. So for the first one, so I'm going to first using a very brute force solution, and then I'm going to improve that. So here I'm going to do root to be the root. So this is our initialization, and then I'm going to implement a hyper function. So the hyper function, so self, so accepts 3 arguments. One is the root, one is idx, and the other is the target, right? So we want to check if we can find the target or not. Target. So if you are familiar with binary tree, right? So here, if the value indexed using 0, and then the left subtree will be 2x plus 1, and the right subtree will, or the root node for the right subtree will be 2x plus 2 if they exist, right? So this is nothing but just indexing the tree nodes, right? So here, what we do for this, we want to check if the target is in the tree. Now let's check. We don't care about the values if it's contaminated or not, right? So in this sense, this problem is not a fantastic problem. So first, if not root, nothing, right? We just need to return false. It's impossible for target to be there. And then if the root is there, if idx equals target, then we just return true. Then we can do recursive call. Then we are going to do DFS to the left subtree and the right subtree. So then if, so self hyper root left and idx times 2 plus 1, right? That's the index for the left subtree. Then target. If or, so I'm going to copy this and change this one to be right, and this +1 to be +2, the target, right? If one of those is true, right? So we're going to return true. Otherwise, we just return false. That's the overall. So that's the hyperfunction. Then for the last the find method, we just need to return self hyper. So root. So root starts from 0, right? Then target. So you can check this solution. So here, let me run it. Root is not defined, so you have to self root, right? Yeah, it passes the 3 test cases. However, if you submit, it's going to time out. So let's wait. The time limit exceeded. So the reason is that each time we do a find, actually we traverse the whole tree. So if the tree is very large, and then each time basically the time complexity will be O of the number of nodes, and then so the number of calls of find times the number of nodes would be a large number. That's why it got time limit exceeded. So that's the one potential solution. However, this does not pass. However, it tells us the essence. So here actually we don't need to do this for everyone. So we just need to index the tree once, right? Index the tree once, and then we just need to check if target is a valid index. That's it. So for this, we can use a membership check. That is, we are going to use a set. So now let me implement here. Let me change this one to be not time limit exceeded. So now for this, I'm going to change this one to be the original one. So now what we do? So we can do self root still to be the root. Then I'm going to introduce another data field called index set. So originally it's an empty set. Then I'm going to not finished yet. So I'm going to write a pass here. So I'm going to write a hyperfunction again. But this time I have a root, I have index. So I don't need to accept the third argument. So what we do is this. So if not root, just a return, right? Otherwise, what we do, because the root is started from index 0 or current index. So what I'm going to do is self index set. So add this index, right? Then what do we do? So we do DFS towards the left subtree and the right subtree. So that is self hyper root left. So because we have already checked the if, right? So this is legitimate. So we can do 2 times idx plus 1. So similarly, let's copy this one and make some modifications for the right subtree. So here I'm going to write it right, and here is 2. So you can think of this hyperfunction as a worker, which modifies the index field. So in order to just use one pass, actually we can do this call when we do the initialization of the class or class object. So that is if root. I don't care if it's contaminated or not. I'll just run the hyperfunction self hyper. So the root and 0. That's it. So once you do the initialization, you are going to get index set. So that's actually the whole work. So in initialization and in this hyperfunction. So when we do this find, it's nothing but a membership check. So we want to tell in self index set. That's it. So this way, we just need to call this hyperfunction once. So when we do the initialization, and then when we do the find method to check target, so it corresponds to a membership check. So membership check for a set is a OM operation, right? So now let's examine. Yeah, it passes the 3 test cases. Now let's look at the generic case. Yeah, it passes all the generic case. So with that said, I guess we have finished the coding. So here, again, let me come back to the very beginning. So the point for this problem is that only the structure of the given tree matters, no matter it's contaminated or not. So in this sense, this problem is not a wonderful problem. And this is the one point I want to make. Another point I want to make is that for this problem, you can write in terms of recursion. So this is very clean, very short. Also, if you like, you can write in an iterative format. The reason I start with the recursion is due to the fact that the tree or binary tree here is a recursive data structure. You can think of recursion when we do this. So here, if I implement another one, I can also do it in an iterative format. So you can do DFS or you can do BFS. So here, let me call this B1. So how do you do this? So same thing, if not root, I'm going to return, right? Then what do I do? So I can do AC. I can use, let's use stack. I can use root, right? So here I can do something like this. So this is the IDX. And then it's the standard while loop. So while S, so we have node and the index equals S on pop, right? Then what we do is self index set. So we are going to add this index, same here, right? So now what we are going to do is to check the neighbors. So if node right, so I'm going to S append. So two things, the root right and the index 2 times IDX plus 2. And then if node left, so I'm going to do S append. So root left, so 2 times IDX plus 1. So that's it, right? So this way you are going to modify the self-index set. So because I have changed this one to be V1, so when I call this one, essentially I'm calling this iterative format. Let's check that. Memory limit. So let's see. Yeah, I guess for this this one, because I'm using this stack, it might have this this problem. Let's see the test result. Run it. This way, memory result. Let's see. So we may do this. So index that. That's interesting. So now let's see if IDX. So yeah, I guess this is due to when we save this root, this actually use a lot of memory. Okay, so now I guess for this problem, we'd better to stick to the recursion format. But here, what let's see, we use this one, change this one to be iterative. So here, yeah. So this is the one thing. So though it's not passing the space limit, so this is still okay. So notice that here in this iterative format, I'm pop from the tail and append from the tail. So this corresponds to DFS. Meanwhile, I wrote here first right and then left. So it corresponds to a certain order of traversal. For example, if you have a tree like 1, 2, and 3, then first you get a stack that is 1, then you pop that, then you do this, and then you right, you add to the stack. So you're going to have 3, and then you have 2. So then you pop, you get 2, you get 3. So 1, 2, 3. This corresponds to pre-order traversal. So this corresponds to pre-order traversal actually. But if you switch the order of left and right, still okay, but it's not pre-order traversal anymore. So this is the one thing. Another thing is this. If you I'm going to change some, so v2. So if you do, let's see, let me just use this as, actually it's not very good, right? So I pop left. So here I can use it as a collections deck. So this basically I pop from the left and then append from the right. So this corresponds to a quill structure. So this will correspond to BFS, right? So with that said, I guess we provide sufficient information for this problem. For clean solution, you can delete these two methods. So here, let me delete that, right? Due to space constraint. Let me run it again to make sure it works. Yeah. So with that said, I guess that's it for the current video. If you found this video useful, you're welcome to share with your friends or your classmates as a support of this channel.